So this is a introductory video about equilibrium and about using Le Chatelier's principle to make predictions about the changes in concentration, changes in temperature, changes in pressure for an equilibrium as you add or remove materials or temperature. So we're going to start with the rate of reaction because rate is a word used in equilibrium. And a rate is the change in concentration over time. Just like the rate of exchange is how much we exchange things over time. So it's basically a ratio of concentration over time. And so in this simple reaction, we have a fluorine molecule separating into two atoms of fluorine. And during this change, the number of fluorines will increase over time. And at the beginning, the rate is the slope here is very steep, which means the rate is steep. And then over time, as fluorines have already reacted, there'll be fewer and fewer changes. And the production of fluorine atoms will decrease. So we see this same change happening here. Now, when we talk about a rate of reaction, we adjust the rates as if they all had a coefficient of 1. And so I just want to know what one fluorine is doing. So I multiply my rate by a half. And now these two rates are equal but opposite. And so because my fluorine atoms are being created and my fluorine molecules are being lost, I want a positive change. And so I've accidentally put a negative here, but the negative, in fact, goes here. So here it's done correctly. One more time. The coefficient tells you how much is changing, and you can see that being graphed out. I've only lost 1 of my nitrogens over time. I'll have lost 3 hydrogens over time. And over time, I'm gaining 2 of the ammonias. And so here I have these rates of change. So that's what you do. When there are losses, you use negative values to change it to positive. And when there are gains, you use positive numbers to do that. Okay, well, traditionally we only cover forward reactions, which is like burning. If you burn anything, it goes to ash, it can't go back, you're stuck with that ash and you can't ever make wood, which is why we're having problems with CO2, with global climate change and ocean acidification. But we're about to look at when there's both forward reactions and reverse reactions, and we can write that as one reaction with a double arrow to indicate that H2 and I2 go to HI, but HI also goes back to H2 and I2, and you'll have some kind of mixture of products and reactants in the same reaction vessel. And we call this equilibrium. Definition of equilibrium is the state of balance in which the rates of the forward and the rate of the reverse reactions are equal. And so in these acrobats, we see that they are trying to maintain a balance by shifting their weight slightly to maintain essentially an unchanging system. And so the concentrations will remain constant, but they don't have to be equal. Same thing happens here. They want more people on the right than they do on the left, and this will allow them to maintain their balance. And so it all depends upon the rate of change, which we measure by something called the equilibrium constant. So when an equilibrium is equal, there's a balance point, and I could actually measure the concentrations of the products and reactants, and they should be unchanged. So this would make a constant ratio. And you use a K to indicate that there's a constant, and that K is defined as products over reactants. The K may be augmented by having these other symbols that tell me that we're using concentration, that we have a solid that's breaking up, that I'm dealing with an acid. So as long as there's a K, this piece is always the same. Here we can use molarity values to produce a K, or we can use atmospheres or partial pressure to achieve K. But we do not use mass or liters to create a equilibrium constant. So for this reaction, it would look like this. Here are all the products. Here are all of the reactants. And so this would be my products over reactants. Notice there's multiplications in between all the symbols. This gets a little unwieldy, and we have a abbreviating nomenclature with exponents or powers. And so we're going to simplify this so that it looks just more, we can handle it easier. Okay, so in review, which is not true during a chemical equilibrium, are the rates of the forward and reverse equal? Well, that's true. Are concentrations of things equal? No, that's not true. That's the most common misconception, is we're trying to make the amounts equal. We're not trying to make the amounts equal. We're trying to make the rates equal, and that means that we'll end up having a constant when we do. So one of the tasks you'll be given is to write an equilibrium constant. So we have to identify the products and the reactants. Which side's the products? And where would that go? On top or on bottom? That would go on top. And then obviously these are the reactants, and they would go on bottom. Again, I've exchanged the coefficients for exponents because the coefficients means I have more than one of them. And instead of writing each of the 3 waters, for example, I'll just say water 3 times with my exponent. Another question is it product favored or reactant favored? And so the KEQ is equal to products over reactants. Since it's 1 over 1,000, then I have 1 product for every 1,000 reactants. And so what's favored? The reactants are favored. So here I have reactants favored in this reaction. And then write it as Kp instead of Kc. And all you do is switch the brackets for pressure symbols. And so instead of these brackets, I will have these pressure symbols that I use. The exponent is sometimes written at the end. It's sometimes written right above the P. It's a little hard to write without handwriting it. All right, so what do we know? Equilibrium is when the 2 rates are the same. But sometimes the rates come out of sync. For example, what if I added more molecules to the forward reaction? Well, there would be more collisions. If there were more collisions, then I would increase the rate at which the change was occurring. Well, now it's out of balance, and everything would have to come back into balance because I have altered the equilibrium. So when you add something, you create a faster reaction, and now things need to change to take care of that. And sometimes you can remove molecules, which slows one of the rates, and you have to go back to balance again. So the way you do that is basically these particles will readjust to get to a new rate, but go to exactly the same equilibrium constant again. So the equilibrium constant only changes if temperature changes drastically, and otherwise all of the changes we're about to see will not really change the equilibrium constant, which will always be the same. So Le Chatelier's principle says that if you make a change that causes stress, and now you got to undo the stress, and I like to show that as a balance beam. So here I have my reactants and my products all balanced, which means that in this analogy that the 2 rates are equal, that the changes between the reactants to products and products to reactants are the same. But if I add more CO2 and increase the amount that's there, I'll have more collisions, and therefore I'll have more reactions. So now the rates are different and it's unbalanced. So in my balance beam analogy, the balance has shifted to so that the products are too heavy. Well, Le Chatelier's principle suggests that the equilibrium will undo that change, which makes sense. The CO2 will now react more with the H2O since there's more of them. And as a consequence, I'll create more of my reactants. So how do I undo this change? How do I get the balance beam to shift back? I make more reactants, which increases their mass. And to do that, I needed to react with the H2O. And so the H2O will decrease as well. So more reactants and less H2O puts this whole thing back into balance. And so an increase in the opposite side after adding product. And my analogy, my memory device is if you add, the equilibrium shifts away. So adding CO2 shifts towards these reactants. We're just going to do a couple more of these. What if I added extra H2O? What would happen to the balance beam? It would be too heavy on the reactant side. How would Le Chatelier's principle suggest that we re-establish balance? Let's get rid of some CO and let's make some CO2 and H2. And that would put it back into balance. Okay, and heat is on here because apparently I should have had heat on this reaction, but we'll see that later anyway. Another possible change to this equation is to remove H2. And so at the beginning, they're all balanced. I take away some of the H2, which makes it smaller. Now there's fewer reactions. The rate has gone down. It's unbalanced. Because I reduce this, it goes up. And so I need to re-establish equilibrium. And to do that, I'll have to make more H2 and reduce the weight or the amount of CO and H2O to allow it to come back into balance. My memory device for this is if you take, it goes towards. So I took away from the H2 side, and so I'm going to shift some of the mass to the H2 and the CO2 side. One more. What if we add heat? So let's say heat was on this side, which is where it should be. What happens when you add heat? So that'll increase this to get bigger. That'll shift it so that this side is bigger. And then we go through the same process of removing and adding to get it back into balance. And again, I added, and so I move away. So I moved more material to this side so that I could come back into balance. If you increase, it shifts it away from the side you added it to. If you decrease, it shifts it towards the side you wanted it to go to. And then pressure acts just like concentration. If we add more pressure, that's like adding more molarity. We'll spend a little more time talking about pressure in a second. Please remember that exo means heat is a product, endo means heat is a reactant, because it may simply be listed that way and not with heat in the actual equation. Catalysts make a reaction rate go faster. Here is the trick problem. If you see an S or an L, you can't use it. It's not part of an equilibrium constant. It's not part of Le Chatelier's principle. They don't really have concentrations or pressures. So, and then of course, if something is not part of an equilibrium expression, then it's not going to affect the equilibrium. So what would the equilibrium expression look like here? It would be products over the reactants. But this is why it's a little tricky. Which things shouldn't I have in this? Should I have solids, liquids, aqueous, gas? Which ones can be actually measured as molarity? And so solids and pure liquids cannot be measured in molarity, and so there's no reason to have them in the equilibrium constant, and so they're not part of the equilibrium change either. But remember, gases can actually have a volume, and so that means that they can have a concentration. So here, let's say I have this whole equilibrium. If I added more water, what would happen? Nothing. There's supposed to be enough water for the reaction to take place. What happens if I made this more pressure by adding some more nitrogen gas, and then nothing, because that substance is not part of the equilibrium, and so it wouldn't change the number of collisions that would happen. Okay, so here's what you're supposed to remember. Add goes away, taking goes towards. And the questions would be, which way is it shifting, left or right, products or reactants? What will increase, what will decrease? So in my first question, H2O goes up. Which way will it shift? So shifting goes away. If I add, it'll shift away. So I'm going to shift to the products because I'm getting away from my water. Well, if I shift to products, what does that do to one of the products? That makes that product increase. And another of the products is heat, so heat will also increase. Okay, your turn, you try. You can stop the video. We're reducing the amount of chlorine, which will change the reactants or products. So which way will it shift? Will it go away or will it go towards? It'll go towards because we removed it. That's the taking part of that memory device. We've taken it away. We're going to shift this way. That means it'll shift to reactants. So what will happen to the products if I'm shifting towards reactants? They'll decrease because I want to move some of that mass to the other side. And this time heat is over on this side. That's a endothermic reaction, so heat will increase too. Sometimes I tell you colors. So these are actually pretty close to the actual colors of substances up here. So what if it's brown goes to clear? Now these are gases, and you added more pressure. So more pressure means, oh, I'm out of order here. But more pressure means that it collapses, gets smaller, which increases the concentration. So if I increase the concentration of 2 particles have to collide versus 1 particle has to collide, which one will have a greater rate? Well, if I condense where these 2 particles are, they're more likely to find each other and more likely to collide. These are not interested necessarily in colliding, but they're going to increase their rate of reaction a little bit too, but this will increase more. And so which way will I go? I'll go towards my products when I increase pressure. I'll show you a little video, a little figure over here to help you. If I'm going to our products, what will happen here? That'll decrease, and the color will get less brown because this was brown in color. So here's a large container, and let's imagine my N2 is inside here. If I shrink it, bloop, then now the particles find each other more often, and so they shift over here. So greater pressure favors the side with the fewest gas particles. So we increase pressure. The side with the most particles was the N2O4. So let me get to that. So greater pressure favors the side with the fewest particles. This has the fewest particles, 1 gas particle, 2 gas particles. You do have to pay attention to the G as well. And less pressure would favor the side with more gas particles. So if the question said less pressure, the reaction vessel would get more brown. All right, same thing. You should stop the video and make choices here and see whether you're right or wrong. We have not talked about pH yet, so these pH questions are not that helpful. Okay, it's easy to get stuck here at the beginning. H plus is actually adding this H3O1 plus. So if I added more of this, what would happen? So please stop the video and I'm going to keep going. Okay, so adding goes away. So I will be moving away from that H3O plus. And that would make me go towards reactants. The F minus, which is a product, would decrease. And the green color would increase. And what about heat? That would decrease. In the pink one down here with CO2, this is what's happening with our acidifying oceans, is all that CO2 we've produced for centuries is making this carbonic acid. So more CO2 will shift away. That'll make more products. That means that we'll increase the product of carbonic acid, and it turns out that the pH will go down. If we add more heat, which is what this says, increased temperature, will shift away. That will shift towards reactants. It will make the OH decrease, and that will make the pH increase. That was badly done. And finally, catalyst is not going to have any change because both the rates of the forward and the reverse rates are the same. So there's no change when you see a catalyst. Okay, quick little review at the end. Here's our equilibrium. We increase concentration of water right there. Describe all the changes. We decrease the concentration of pH3. Describe the changes. They're the same. Increase pressure. Okay, well, there's 2 gases and there's 4 gases. There's 6 gases on this side and 3 gases on this side, and the solid doesn't count. So if you increase pressure, you shift away from the side with the most pressure. There's heat, it's endothermic, so decreasing temperature will shift it towards the reactants, and if you add catalysts, there will be no change. All right, I know I did that last one really fast, but you could stop it and come up with your own changes, and it's not very well done for online learning. If you have any questions, see me on Remind or email me. I appreciate you spending time on this video. Thank you.